Hello and welcome. My name is Nate Hayden, and I am Levo's Research and Development Director. This video is the first in Levo International's training series on fertilizer use in hydroponics. Thank you very much for listening to this video. I'd first like to start off by thanking the Northeast SARE, who provided funding that enabled us to carry out research optimizing our fertilizer protocol and also to make these training videos. First of all, we have the most famous process in plant nutrition, which is photosynthesis. And this is a key concept to understand anytime that we are talking about plant nutrition. And so photosynthesis is the process that plants use to take up carbon dioxide from the air and water from their roots. Then, with an infusion of light energy, they're able to convert these inputs into sugar. And another byproduct of photosynthesis is oxygen gas, which helps our atmosphere remain habitable, and it's really a nice output that's worked well for us as human beings. But the main byproduct of this process for plants is that they get sugar from this. However, sugar is not enough for plants completely. It's a key energy source for them, and it's very critical, but it's not enough. They also need nutrients of all different sorts. And as with human nutrition, some of these nutrients are needed in large quantities, while others are only needed in small amounts. And plants need to take up these nutrients from the soil or from the nutrient solution in hydroponics. They can't get them from the air. Plants can't move very easily other than the fact that their roots can grow, so it's critical that they have access to these nutrients in their environment. And these nutrients can come in different forms, and they need to be in different concentrations for plants. As with human nutrition, we don't need as much of some things as we need of others. And those things that plants need a lot of are referred to as macronutrients, or macros I have here. And those elements, or those nutrients that are only needed in small amounts, are called micronutrients or micros. And here is a picture showing all these different elemental symbols, and here's a list of all the elements that plants need. And when we think about a hydroponic nutrient solution, these nutrients will all be necessary to include in that nutrient solution, whether it's something that we're adding directly or something that's already present in the source water. So the question is, okay, we have these elements, these nutrients in our nutrient solution or in the soil. How do they go from that into a plant root? And this can happen in several different ways. The first example here I have is passive transport, which means that no energy is being expended by the plant to induce the uptake of these nutrients. And so this can happen with good old-fashioned diffusion. So we have here these particles outside of the membrane, which is in this case a plant cell, a root cell. And you can see that they move from high concentration to low concentration. So this membrane is open enough, it's permeable enough to allow this to happen in some cases where we have movement of particles across this membrane. And then the plant can make this also easier by setting up specific channels that select for different types of particles. So for example, it might select for potassium, or it might select for calcium and allow those particles to freely move through. Again, this is passive transport, so they have to move from a higher concentration to a lower concentration. It's very unlikely that they're going to move in any meaningful way in the opposite way without energy being input. So they'll move this way, and we provide this channel. The other important thing to remember here is that you can also have various degrees of selection at this level here. So you can have, as I said before, you can have a channel that only allows potassium, Or you could have a channel that only allows positively charged particles under a certain size. So this would allow calcium to come in. It would allow also magnesium and ammonia to come in through the same entry point. Finally, we also have the option for plants to use active transport. And again, this is typically when they already have a high concentration inside and they want to move stuff inside anyway. And they can't rely on diffusion, whether facilitated with a channel or not, and they have to actually expend energy to import. But the same general concept applies around the selectivity of this and whether, if this can import just one type of particle or multiple types. But again, it's important to remember that because sometimes these channels are selective for specific attributes of a particle, the charge of a particle and the size of a particle, even the degree of charge of that particle are all important considerations to keep in mind. And that's because nutrients need to be balanced in a plant's environment. So I'm talking about the nutrient solution in the hydroponic context, or talking about soil. So it doesn't only matter that there's enough of everything, the nutrients also have to be balanced. And here's an example, an illustration of this from this one paper, where you see, and again, this is what I'm talking about, you have a potassium specific transporter on the top, which you see there's a mix on the left is the outside of the cell and on the right is the inside. And there's a mix of, in this example, we have some potassium, we have magnesium, which is Mg, the potassium is K, and we have ammonium, NH4 plus in this example, ammonium. And so any of these, all these are positively charged, and all of these are present here, but this transporter is specific for potassium. And so that's going to be taking up only potassium. And then on this, in the bottom here, we have a non-specific, an unspecific transporter, and that will take up any, in this case, positively charged particle. And so we have a mix of those moving from a high concentration outside of the cell to a lower concentration inside the cell. And so you can say we end up with a mix. In this example, the plant successfully transported potassium, magnesium, and ammonium into its cells. So this is the successful example. This has a balanced diet, if you will. This is a balanced amount of nutrients outside. However, in this example, we have an abundance of potassium. So magnesium is still present, ammonium is still present, but the potassium is present at a higher level. And so again, at the top, we see more potassium coming in a little bit because again, there's just more of it available outside. So it's going to get even more easy for that channel to work and bring in potassium. But then at the bottom where we don't have a specific transporter, we have a non-specific one. We still see potassium dominating because just the pure odds of potassium interacting with this transporter are higher. And so if we have a lot of potassium, we're going to have a lot of potassium inside the plant. But then that's going to prevent magnesium and ammonium from coming up into the plant, even though they're present outside of it. And so this is why it's critical to make sure that we have balance, because even if we have enough of everything, if there's too much of one thing, that can prevent the plant from being able to uptake all of these other important particles that are critical nutrients. And we see a similar example here. It's got cut off a little bit, but the same thing can happen if we have a high magnesium concentration or high ammonium concentration. Any of this, it's not specific to potassium. It can happen in any of these cases. Another really important thing to think about is the pH. And when you're looking at a nutrient solution, the pH is really important because it dictates the availability of these compounds for uptake. So the pH is a measurement of the acidity or basicness of a liquid solution. So it's based on the concentration of hydrogen ions that are free in the solution. And a pH of 7, as you see in the middle with the dotted line on this figure, is considered neutral. It's a neutral pH. And if you go below 7, it's acidic, and above 7 is basic. And so every element in this case has a different optimal pH range for uptake. And you can see that represented here, where the red is a low availability, so it's not really easily uptaken at that pH. Yellow is intermediate, and green is high. It's very efficient in uptake at that pH, which is what you want. And so you see it's not a simple thing necessarily to set up that pH, because every single one of these elements has a different optimal range for availability for a plant. However, between 6 and 7.5, really maybe you could go as far as 5.5 and 8, but really 6 to 7.5, everything's in a range that's pretty much acceptable for uptake. If you start getting too low, you're going to have problems with nitrogen, phosphorus, potassium. And if it goes too high, you're going to have problems with a lot of the micronutrients, such as zinc and iron. And you start having deficiencies, which can cause a lot of serious problems with your plant. So you want to make sure that pH also matches in addition to the nutrients. So again, it's not just about what is there. It's about, is it in the right balance, and is the pH set up so that the plant can actually take these things up. So to get a little bit more specific, we primarily use J.R. Peters, Jack's Nutrient Blend. They come in a Part A and Part B. And I do want to note that the J.R. Peters has supported us with donations in the past. We've used them with a lot of success, and they're one of the best products that we have found. And it's really convenient because it comes in this mix that contains all of those different components. And so it's really critical when you're looking at any fertilizer mix to look at the nutrition facts, and to make sure you understand what are the different components of that fertilizer to make sure you're mixing it well. So the first thing that jumps out are the three numbers listed. So we have Part A, 5, 12, 26, and Part B, 15, 0, 0. And the three numbers are called NPK values because they refer to the percentages of nitrogen, phosphorus, and potassium. So there's 5% nitrogen, 12% phosphorus, and 26% potassium present in this. And so in the Part B we have, which is calcium nitrate, we just have nitrogen in 15%. And also it's important to realize that it's not quite as simple as this for phosphorus and potassium, because they're measured not as pure phosphorus and potassium, but as P2O5 and K2O for so they're not, but there's a little bit more complexity there, but essentially it's the amount of nitrogen and the amount of phosphorus and the amount of potassium. And it's when you get a fertilizer, the description, or you can also look online a lot of times, which is where I got this picture from. The description of a fertilizer is typically on the label on the back of a fertilizer bag, and this provides much more detailed information about the percentage of all the nutrients, not just the NP and K. So as I mentioned, all these are important. So you need to know how much sulfur is present, how much boron, also those micronutrients, right? Like iron, copper, manganese, molybdenum, and zinc. These are also really critical to consider. And oftentimes, as in this example, they provide a little bit of instructions and suggestions about how much to add. And this is really critical information for deciding fertilizer application rates. So this is the starting point when we look at a fertilizer and decide, okay, how much are we going to add at what times. As I mentioned before, as you look at here, the NPK percentages are not really as straightforward as they necessarily seem. So nitrogen is in different forms. And so this is the percentage of nitrogen. So there's 5% nitrogen out of all of this. So 5% of the weight of this bag is nitrogen. In this case, it's all in nitrate. So 5% of that is nitrate. So 5% nitrate, nitrogen. But sometimes you also see ammonia or other compounds. And it's important to look at that, because if it's not nitrate, you have to be much more careful, because nitrate, plants can take it up and they can store it, and it doesn't get toxic as quickly, but you have to be much more careful with things like ammonium application because they get toxic at lower levels and plants can't store them as easily. They need to incorporate them immediately into their final products in the plant. So that's just a little warning there. And then if you look at the percentages of phosphorus, in this case it's in phosphate, so P2O5. So if you want to figure out how much phosphorus is present, you'd actually have to convert this percentage to phosphorus. And the same thing we have with potash, K2O. You have to make that conversion if you're trying to calculate how much potassium specifically. So it's called NPK, but it's a little bit more complex if you're going into the actual calculations, which is outside of the scope of this video, but it's important to keep that in mind as you're thinking about these different fertilizers. And so, in summary, plants use photosynthesis to make sugars, but then they also need macronutrients and micronutrients, and they get them from their roots and from the nutrient solution in hydroponics or from the soil in a traditional system. And so balancing the concentrations of nutrients is critical, and it's also important to look at the pH and the environment that these plants are in as well. And so we will go more into our specifics in our next video about how we actually design a nutrient protocol in terms of how much we're adding and how frequently and how this might differ with different crops. But thank you very much for listening to this video, and I look forward to having you join the next one. Have a good rest of your day.